So it's not very likely that if we were construct a confidence interval that we would not know a population mean, but know a population standard deviation. Remember, to find a population standard deviation, this is calculated using mu, which is what we're looking for. So it's not very likely that we would know sigma, but we not know mu. So in reality, most of the time when you do a confidence interval, you do not know what the population mean is, and you do not know what the population standard deviation are. These are both unknowns. So we need to find another way to assess to figure out a confidence interval when I do not actually have a sigma. Okay. Skip through a couple slides here. So we need to talk about something called a student t distribution. So when we are constructing a confidence interval where your population standard deviation sigma is known, well, we can use z-scores. So remember, we're looking at a distribution of x bars. So when we find that z-score, we're looking at a z-score of x bar minus the mean of all my x bars divided by the standard deviation of all my x bars. But what that came down to is that that's x bar, and the mean of your means is equal to your population mean. The standard deviation of all your means is the standard deviation of the population divided by the square root of the sample size. So what we have is that we have that sigma, so we can have a z-score. So we have that, and also what we know from central limit theorem is that we're going to have that these population of z-scores is going to have a normal distribution. So because we have a normal distribution, we know how to deal with a normal distribution. So we have a new problem here. So like I said, it is rare that we would know the value of sigma while needing to estimate the value of mu, because we use mu to find sigma. In practice, it's more common that sigma will be unknown, so we will not know a population mean. So when we don't know the value of the population mean, we replace it with a sample standard, which means we're going to replace it with an S, or our sample standard deviation. So when we don't know what the value of sigma is, we replace it with the sample standard deviation S. However, we cannot use z-scores because the quantities that we're looking for are going to be written like this. We're going to have x bar minus mu, but instead of a sigma, we have an S. And if you remember, S tends to underestimate. There's an important letter and under an estimate there. They tend to underestimate this. So your sample standard deviations tend to underestimate your population standard deviations. So they're bad. They're very biased is the problem. So I can't say that my distribution of x bar minus mu divided by s divided by the square root of n, all of these, it's not going to have a normal distribution. It's going to change a little bit. And what we're going to get is a different kind of distribution, which is called your student's t distribution. So the guy who came up with this, his name was Student. So that's why it's a student's t distribution. Okay. So there are actually different student t distributions, and they're distinguished by the quantity related to the sample size, which is called your degrees of freedom. So when using the student's t distribution to construct a confidence interval for the population mean, the number of degrees of freedom is one less than the sample size. So it's a little complicated, but a degree of freedom is like how many variables are free to kind of wiggle around. Is kind of the idea here. So we have something kind of fixed, but everything can move around. So we build these degrees of freedom. So this is just showing you that this is when we have 1 degree of freedom. So my sample size was 2 here. The blue line, that's 3 degrees of freedom. So my sample size was 4. Then we have the yellow, which is 8 degrees of freedom. So my sample size was 9. The green line, that is 20 degrees of freedom. So my sample size is 21. But as you're seeing, as the sample size changes, so does the shape of the curve. And like I said, going like this, we see that the purple curve has the least amount of degrees of freedom. It's squished down a lot more. So it's like it gets squished. And what happens is it has to contain the same area. So even though we squished it down, that means the tails have to get fatter. So it changes the shape a little bit. And then the blue one's a little taller. So because it's taller, the tails can go down a little bit. So its tails are a little smaller. But eventually what you're seeing here is this black line is your standard normal curve. And what we expect to see is that this will start to approach a standard normal curve. So we have a few more images on this side for it. So a student's t distribution is symmetric and unimodal, just like the normal distribution. However, there's more spread. It's more spread out, pulled out. Like I said, this little dotted line. So the black line is a z curve. And this purple line, that is your student your t curve is really what it is. And like I said, because S, sample standard deviation on average, is a bit smaller than your population standard deviation, it causes the distribution to get kind of spread out like this. So it's spread out over a larger area, which is why your tails are a little higher. So it's spreading these tails out further. Also, since S is random, replacing sigma with S increases the spread. So basically, we're dividing by something smaller, meaning that my z-scores are kind of like getting bigger. They're getting bigger, so they're getting more spread out. But we see here that, like I said, all the black curves are the z-curves. Here we have more degrees of freedom, and this little dotted curve here is my t. But you see, this is a little closer to looking like the z-score, and at 10 degrees freedom, it's even closer. So the difference between the t distribution curve and the normal distribution curve is greater when the degrees of freedom are smaller. So when we have smaller degrees of freedom, we're further from the z-score or z-curve. The bigger my sample size is, the bigger my degrees of freedom, the closer that my t distribution is to the z distribution. So like I said, when the number of degrees of freedom is large, S tends to get close to sigma. So then t distribution gets very close to the normal distribution. So it's this. As n gets larger, so as we send it out to infinity and get larger and larger, our samples, remember law of large numbers tells me that my sample size, my sample means, sample standard deviations, all that stuff is going to get closer to what it looks like in the population. So my sample standard deviation starts to match the population standard deviation, which then means that my t-scores, which your t-score is actually this. We were actually just saw your t-score. So that's your t-score. Remember, this is your z-score. So because S and sigma are getting closer to each other, that means T starts to look like Z. So there's actually kind of a point where we don't even have to really use a student T distribution anymore. So once again, when we talk about critical values, the same kind of rules are going to apply. If this is 95% level of confidence, well, that means that alpha is going to be 1 minus 0.95. So alpha works exactly the same, meaning we have 5% left over. If we divide alpha in half, that means we have, instead of 5%, we have alpha in half is 2.5%. So we have 2.5% in each tail. So that means that this t-score here is not just t alpha divided by 2, but it's t alpha 0.025 because it's representing the area in the right tail, which means this one is negative t 0.025. So the notation for these t-scores are going to be just like z-scores. But this is also a critical value. So t-scores and z-scores can both be critical values. All right. So if we're trying to figure out, you're going to have a table that looks like this. So let's say we had a confidence level of 95%. This area in the right tail is going to be 2.5%. And we were trying to look at this and try to figure out what my t-scores are. We would be looking at, there we go, I was like, completely could not find it. We'd be looking at this area right here. So it says area in the right tail, 0.025. So like I said, we're going to keep using that area in the tail. So this works a little differently than a z-table. So this is your t-table. Your t-table is going to need that area in the right tail, and it's going to need degrees of freedom. So let's say my sample size was, let's say 3. That means my degrees of freedom would be 2. So I'd look for 2 degrees of freedom. And this here, that would be my t-score. So if you remember with the z-score was 1.96. So if you notice here that these t-scores, if I had 1 degree of freedom, it's at almost 13. If I have 3 degrees freedom, then that t-score is at 3.1. If we get to 200 degrees of freedom though, we get 1.97. Eventually, this gets closer and closer and closer to looking like that z-score. Okay, so I'm gonna actually take us to the real t-table here in a bit, so you can see what this really looks like. But we have a simple random sample that has a size 10 and is drawn from a normal population. So that's that same kind of rules apply, as that as long as the population is normal or my sample size is greater than 30, then we should have a normal distribution of t-scores. So a lot of the same rules apply here. It's just like I said, it's just that you have a variety of curves to look at with the t-scores, where z-scores is just one curve that we look at. So we want to find the critical value for t alpha divided by 2. So we just said for 95%. So we already said for 95%, that is t 0.025. We have 5% left over, half it's in the tail, that's 2.5%. And we don't like writing percents as percents, we write them as decimals. So let me show you what the t-table looks like. So if you remember, your z-table is always area to the left, this is always area to the right. So if we have a sample size of 10, then my degrees of freedom are going to be 10 minus 1, or 9. So let me make this just a little bigger over here so we can actually see these numbers. So we need to look for 9 degrees of freedom. When you see degrees of freedom, there's 9. We have 0.025 in the tail. That's going to be this right here. So what we're going to get is that my t for 0.025 would end up being 2.262. Okay. So let me just change this problem just a little bit to show you how else we can do this. So just to go through this one more time. Let's say we have a sample size, let's pick 20 now. We have a sample size of 20. And let's say we have a confidence level. We'll pick 99%. So remember, that is 99% in the center. So alpha is 1 minus that 0.99, which is going to be 0.01. There's 1% left. If I divide that by 2, I'm going to have 0.005. So this area over here in this right tail is 0.005. And the t-score that we're looking for is t 0.005. So I've got this one part here. Degrees of freedom. And my degrees of freedom are my sample size minus 1. I have 19 degrees of freedom. So there's my 19 degrees of freedom. I need to look for the right tail. I need a 0.005, which is right here. And what we're going to have is that t for 0.005 is going to be 2.861. Okay. So another thing just to point out here, going back to something we had said earlier, remember that for a z-score of 0.025, we should have a z-score of 1.96. So that there is that 2% left in the tail. So as degrees of freedoms increases, like I said, we start at 12, we're at 4, we're at 3, we're at 2.7, we're at 2.1, we're at 2.09. Keep getting larger. Here at 60, we're at 2. At 80, we're 1.99. At 100, we're at 1.96. At 200, we're 1.97. So as you see, we're getting closer and closer and closer to eventually we're getting right up to 1.96. Here is that level of confidence. So this also can help you out. So there's my level of confidence. There's my 99. Once again, if we were looking, once again, for that 99% confidence interval, so we had 2.861 as my t-score. The z-score would have been 2.576. So there is going to be, like I said, there's just a little difference in those scores. And each time we may have a different sample size, we really have a different t-score to look at. So we're going to, or different t distribution to look at, we're going to get different t-scores. So sometimes your degree of freedom are not on that table. So you notice that at a certain point, it went from 60 to 100 to 200. So actually, let me go back and show you more of those. Like I said, you're looking along here. And at this point at 39, we're going down up by ones. We go 39, then we go 40, 50, 60, 80, 100. So if you're using the table, and there's different tables out there. Let's say that my sample size was 50. Well, then my degrees of freedom would have been 49. And 49 is not on here. What do I do? What you would do is you pick the degree of freedom that is closest to what you have. So in this case, we would end up picking 50. If I had 67 was my sample size, my degrees of freedom would be 66. Here it's like it's 60, it's 80. Well, 60 is the closest, so we'd pick 60. So we do this up until we got to 200. Well, remember 200 isn't very far from what your z-score is. So what we'd end up doing is that if the desired number is less than 200, we use the next smallest number on the table. So we use what's next to it. If the desired number is greater than 200, use the z value found on the last row of the table. So we're going to just basically just like leave everything at basically a z-score is what we're saying here. So anything greater than 100, we're just going to use z's. So that's if you're using the table. But we do have a calculator that will do us for us. So here we're going to talk about let's first do our first problem. So our first one was a sample size of 10, and then we had 90 degrees of freedom. We had 0.25. We're also going to look at something that wouldn't fit on the table, but I can do in the calculator. So if I had a 95% confidence interval, but my sample size is actually 122, that doesn't fit on my table. We're going to go back like what we'll see at the table and what we'll see with the calculator. If I use the table, this one's telling me that my degrees of freedom are going to be 9. My degrees of freedom here are going to be 121. So this one we had already found. Oops, and highlighting everything but the actual number that I wanted. This is what we had found over here. So this is what we found last time. So we're going to compare that to what our calculator is going to tell us. So according to this, the t-score for 9 degrees of freedom for 95% is 2.262. I'll write that right under it so we can see it better. 2.262. So that is according to the table. So that value was on the table. This one is not. So if we're looking for 121 degrees of freedom, we'd have to use 100. And we'd have to look for that 95. So really, it's just going to be this score here. So we would get 1.984. So this is from the table. So this is why the calculator is going to be useful. For stuff that's not on the table, it's going to give me much better values. All right, so going back to the calculator, if we go to second bars, that's going to take me to my distributions. You're going to see here at number 4, it says, like this is invert the normal distribution, this is invert the t-distribution. So you're going to put that area in. So that area is 0.025. And my degrees of freedom were 9. And notice it gives me that same value, but it gives it to me as a negative. So when you use the t-norm, or invert, not t-norm, sorry, invert t, what it's going to do is it's actually telling you this area here. So this is kind of like what we were doing with, we were trying to use z-scores. The z-scores are just telling me to the left, and I have to convert that to the right. So this is actually telling me that negative t of 0.025 is negative 2.262. But we know that we just want to convert that to positive. And what we're seeing is that this matches the table pretty close. There's a little bit of rounding there, but if I round to 3 decimal places, it's going to be the same. Now, if we look at the other case where my degrees of freedom were 121, remember, it's going to give me the negative score first, so we're going to have to turn it into a positive. So we're going to go to second bars. Oops, I think I hit the wrong thing. Second bars, go to number 4. The area stays the same, but I'm going to put 121 degrees of freedom. Oh, so I think it wasn't working there for a second. It just took it a moment. So here we got 1.984. The calculator says it's going to be, remember, turn to a positive, 1.97. So this actually over predicts it a little too much. And like I said, it's because if I use the table, the best I can look at is actually 100 degrees of freedom. If I use the calculator, it gives me a much better estimate. Actually, let me change that. So this one's off a little bit more, not a huge amount. But like I said, it's a little more accurate when you do this comparison here. Yeah, this one's going to be much more accurate. All right, so we had mentioned this with confidence intervals and we're using z-scores. Once again, we have to make those same assumptions. We have to have the assumption that we have a simple random sample so that each sample is going to have the same probability of existing. The sample size should be n is greater than 30 or your original your population was normally distributed. So note when the sample size is small or less than 30, we must check to determine whether the sample comes from a population that is approximately normal. A simple method is to draw a dot plot or a box plot of the sample to look for skewness or outliers. Okay. So that's just something to look for. You may actually have to go back and look at your original population. So let's just do, like I said, just look for our confidence intervals here. So the only thing that changes, oh, sorry, just the critical values. I thought we were looking for the confidence intervals. We're going to find the critical values once again. So just so we mention this here, this fits my assumption because my sample size is over 30. So that means that T's are normally distributed. My X bars are normal. Here we got a sample size of 15. I can't guarantee normalcy. The distributions could be normal. I just can't guarantee it at that point. So that's just something like to bear in mind in the back of your head that you always really need to check to see if things are normal before you even start trying to do any of this work. Okay, so I'm going to do these with both the table and with the calculator. So here we want to find the critical value for a 90% level of confidence. So we got 90 out of the center. Alpha is going to be 0.1 because that's what's going to be left over because it's going to be 10%. So alpha divided by 2 is going to be 5%. So each tail has an area of 0.05. So when we talk about the t value, we're looking at a t and the subscript will be 0.05. So that is the area in my tail. And remember, it's supposed to be the right tail, so this should come out as a positive number. My degrees of freedom, well, we have a sample size of 63 minus 1. I have 62 degrees of freedom. So if we do B, we're doing that 95% level of confidence. So without having to do the work, I know that's T 0.025. That's what's going to be in that tail. We've seen it a bazillion times. Degrees of freedom will be 15 minus 1. So in this case, they'll be 14. Okay, so I'm going to do the table first, and then we're going to do this with the calculator. Okay. So we are looking for an area in the right tail of 0.05. So make sure you pick the correct one because we have 0.005 and 0.0005. So we need 0.05. So always bear in mind you have to do that. My degrees of freedom are 62. So let's scroll down. Scroll down a little bit more. So we don't have 62. The closest I have is 60. So I'm going to have to use the 60 here. So we see right here that from the table, T 0.05 will be 1.671. All right, so for B, if we're going to do B now, we have 95% level of confidence, like I said down here. So the area in the tail is 0.025. So make sure you pick 0.025, not 0.0025 or 0.25. We want this one right here. And we have 14 degrees of freedom. So right there. So here, T is 0.025 for 14 degrees of freedom is going to be 2.145. All right, let's do this in the TI-84. Okay, so let me clear everything there. So for A, we go to second, bars. We go to number 4, invert the T table. My area is 0.05, and I have 62 degrees of freedom. Just give it a second here. So here it says T 0.05 is going to be, remember, change it from negative to positive, 1.6. Well, if we rounded that's 6698. So that A is going to round this up to a whole 10. So it'd just be 70. So just off by like a decimal place. And like I said, that's because that one was not exactly on the table. If I do my last one now, sorry, it looks like part got cut off at the bottom. One for our stats, or second bars, second bars, there we go. Number 4, now we're looking at an area of 0.25 because that's 95% level of confidence. We had 14 degrees of freedom. And this one should be much more accurate. Let me hit enter. Maybe I've forgotten to hit enter. Second. Sorry, something just was not working right on my end there for a second. So we have T 0.025, and this time we're going to turn that into a positive 2.1, and this one is more accurate, 47. Or sorry, not 47, 45. We do the rounding.